In general, it is not recommended to use one ground rod for 2 buildings and 2 services. According to the National Electrical Code, or NEC, and other industry standards, each building should have its own grounding electrode system separate from other structures. This is to ensure that each building is adequately grounded and protected from electrical hazards. Each service, or power supply, should also have its own grounding electrode system. This is to provide a low resistance path for fault currents and lightning strikes. Using one ground rod for multiple systems increases the total resistance of the grounding system. This can compromise the effectiveness of the grounding and lead to potential safety hazards. With multiple systems connected to a single ground rod, fault currents or lightning strikes may split and flow through different paths. This can reduce the effectiveness of the grounding and increase the risk of electrical hazards. Using multiple systems on a single ground rod increases the amount of electrical current flowing through the rod, which can accelerate corrosion and shorten its lifespan. In some limited cases, it may be acceptable to use one ground rod for 2 buildings or services, such as small, non-residential buildings with a common electrical service, or buildings that are located very close together and have similar soil conditions. Even in these exceptional cases, it is important to consult with a qualified electrician to assess the specific situation and ensure that the grounding system meets code requirements and provides adequate protection. The NEC mandates specific requirements for grounding electrode systems to ensure safety and proper operation of electrical systems. These requirements address the materials, size, installation, and connection methods for grounding electrodes. The purpose of a grounding electrode system is threefold. Firstly, to provide a low impedance path for fault currents to return to the source, facilitating the operation of overcurrent protected devices like circuit breakers or fuses. Secondly, to stabilize the voltage to ground during normal operation, minimizing voltage fluctuations and preventing equipment damage. And thirdly, to provide a path for dissipating static electricity and lightning strikes, protecting buildings and occupants from electrical surges. The NEC specifies several types of acceptable grounding electrodes, including metal underground water pipes, metal frames of buildings or structures, concrete encased electrodes, ground rings, and ground rods or pipes. The choice of grounding electrode depends on site conditions, soil resistivity, and local requirements. Ground rods, typically made of copper or copper-clad steel, are commonly used due to their ease of installation and availability. The NEC requires that ground rods be at least 8 feet in length and 5/8 inch in diameter. They must be driven vertically into the ground, or at an angle not exceeding 45 degrees when rock bottom is encountered. The spacing between multiple ground rods should be at least the length of the rod to minimize overlapping of their effective grounding zones. Concrete encased electrodes, also known as UFA grounds, consist of at least 20 feet of bare copper conductor, not smaller than number 4 American wire gauge, encased in at least 2 inches of concrete. They are typically installed in the footing or foundation of a building and provide a very effective grounding electrode due to the large contact area with the earth. Metal underground water pipes can be used as grounding electrodes if they meet certain requirements, including being electrically continuous and having at least 10 feet of direct contact with the earth. However, plastic pipes or insulating unions can interrupt the electrical continuity of the water pipe, making it unsuitable for use as a grounding electrode. The metal frame of a building or structure can serve as a grounding electrode if it is effectively grounded and electrically continuous. This typically involves bonding the metal frame to a grounding electrode conductor and ensuring that all metal components are securely connected. Ground rings consist of a bare copper conductor, not smaller than number 2 American wire gauge, encircling the building or structure and buried at a depth of at least 2.5 feet. They provide a low impedance grounding path and are often used in areas with high soil resistivity. The grounding electrode conductor connects the grounding electrode to the equipment grounding bus in the service equipment. The size of the grounding electrode conductor is determined by NEC Table 250.66 based on the size of the service entrance conductors. The grounding electrode conductor must be securely connected to the grounding electrode using listed connectors or exothermic welding. Proper installation of grounding electrodes is crucial for ensuring the effectiveness of the grounding system. The NEC provides detailed requirements for the location, depth, and spacing of grounding electrodes. Ground rod should be driven into the ground until at least 8 feet of the rod is in contact with the soil. The top of the ground rod should be flush with or below the ground level to protect it from damage. The resistance of the grounding electrode system should be tested to ensure that it meets NEC requirements. The NEC specifies a maximum resistance to ground of 25 ohms for a single ground rod. If the resistance exceeds 25 ohms, an additional ground rod or grounding electrode may be required. Soil resistivity plays a significant role in the effectiveness of grounding electrodes. High soil resistivity increases the resistance of the grounding system, reducing its ability to dissipate fault currents. Soil resistivity can vary depending on soil type, moisture content, and temperature. In areas with high soil resistivity, it may be necessary to use multiple ground rods or other grounding electrodes to achieve an acceptable resistance to ground. Regular inspection and maintenance of grounding electrode systems are essential for ensuring their continued effectiveness. Grounding electrodes should be inspected for corrosion, damage, and loose connections. The resistance of the grounding electrode system should be tested periodically to verify that it still meets NEC requirements. Any issues identified during inspection should be promptly addressed to maintain the integrity of the grounding system. Grounding electrode systems must be properly bonded to other metal components in the building to minimize voltage differences and prevent electrical shock hazards. The NEC requires bonding of metal water pipes, gas pipes, and other metal objects that are likely to become energized. Bonding involves connecting these metal components to the grounding electrode system using bonding jumpers. The size of the bonding jumpers is determined by NEC Table 250.102. The NEC also addresses the grounding and bonding of separately derived systems, such as generators and transformers. Separately derived systems must have their own grounding electrode system, which is separate from the grounding electrode system of the main service. The grounding electrode conductor for a separately derived system must be sized according to NEC Table 250.66, based on the size of the derived phase conductors. The equipment grounding conductors for separately derived systems must be connected to the grounding electrode conductor at the source of the system. The NEC provides specific requirements for grounding and bonding in various types of occupancies, including residential, commercial, and industrial buildings. These requirements address the unique electrical hazards associated with each type of occupancy. In residential buildings, the NEC requires that all metal enclosures containing electrical conductors be grounded, including outlet boxes, switch boxes, and lighting fixtures. The NEC also requires ground fault circuit interrupter, or GFCI, protection for receptacles located in bathrooms, kitchens, and other wet locations. In commercial buildings, the NEC requires that all metal raceways, cable trays, and equipment enclosures be grounded. The NEC also requires surge protection devices to protect sensitive electronic equipment from voltage surges. In industrial buildings, the NEC requires that all metal machinery, equipment, and piping systems be grounded. The NEC also requires special grounding and bonding requirements for hazardous locations, such as areas containing flammable liquids or gases. Proper grounding and bonding are essential for electrical safety and equipment protection. Failure to comply with NEC requirements can result in electrical shock hazards, equipment damage, and fire. It is important to consult with a qualified electrician to ensure that electrical systems are properly grounded and bonded in accordance with the NEC. The size and type of grounding electrode conductor is determined by the size of the service entrance conductors, as specified in NEC Table 250.66. For example, if the service entrance conductors are number 2 American wire gauge copper, the grounding electrode conductor must be at least number 6 American wire gauge copper. The grounding electrode conductor must be securely connected to the grounding electrode using listed connectors or exothermic welding. The connection must be accessible for inspection and testing. Grounding electrode systems should be tested to ensure that they meet NEC requirements. The NEC specifies a maximum resistance to ground of 25 ohms for a single ground rod. If the resistance exceeds 25 ohms, an additional ground rod or grounding electrode may be required. The resistance of the grounding electrode system can be measured using a ground resistance tester. The ground resistance tester injects a small current into the ground and measures the voltage drop to determine the resistance. The testing should be performed under dry conditions to ensure accurate readings. Regular inspection and maintenance of grounding electrode systems are essential for ensuring their continued effectiveness. Grounding electrodes should be inspected for corrosion, damage, and loose connections. The resistance of the grounding electrode system should be tested periodically to verify that it still meets NEC requirements. Any issues identified during inspection should be promptly addressed to maintain the integrity of the grounding system. Bonding is the process of connecting all metal parts of an electrical system together to create a low impedance path for fault currents. Bonding helps to equalize the voltage potential between different metal parts, reducing the risk of electrical shock. The NEC requires bonding of metal water pipes, gas pipes, and other metal objects that are likely to become energized. Bonding involves connecting these metal components to the grounding electrode system using bonding jumpers. The size of the bonding jumpers is determined by NEC Table 250.102. For example, if the service entrance conductors are number 2 American wire gauge copper, the bonding jumper must be at least number 8 American wire gauge copper. Bonding jumpers must be securely connected to the metal parts using listed connectors or exothermic welding. The connections must be accessible for inspection and testing. Equipment grounding conductors provide a path for fault currents to return to the source, allowing overcurrent protective devices to trip and to energize the circuit. Equipment grounding conductors are typically run with the circuit conductors and connected to the metal enclosures of electrical equipment. The size of the equipment grounding conductors is determined by NEC Table 250.122, based on the size of the overcurrent protective device. For example, if the overcurrent protective device is rated at 20 amps, the equipment grounding conductor must be at least number 12 American wire gauge copper. Equipment grounding conductors must be connected to the grounding electrode system at the service equipment. Ground fault circuit interrupters, or GFCIs, are devices that protect people from electrical shock by detecting small ground faults and interrupting the circuit. GFCIs are required for receptacles located in bathrooms, kitchens, and other wet locations. GFCIs work by monitoring the current flowing through the hot and neutral conductors of a circuit. If there is a difference of more than 5 mA between the current flowing through the hot and neutral conductors, the GFCI will trip and energize the circuit. Surge protective devices, or SPDs, are devices that protect electrical equipment from voltage surges caused by lightning, power outages, or other disturbances. SPD work by diverting excess voltage to ground, preventing it from damaging sensitive electronic equipment. SPD are typically installed at the service entrance and at branch circuits that feed sensitive equipment. There are different types of SPD, including surge arresters, surge suppressors, and transient voltage surge suppressors, or TVSSs. The choice of SPD depends on the application and the level of protection required. Proper grounding and bonding are essential for electrical safety and equipment protection. Failure to comply with NEC requirements can result in electrical shock hazards, equipment damage, and fire. It is important to consult with a qualified electrician to ensure that electrical systems are properly grounded and bonded in accordance with the NEC. The information provided in this narration is for general guidance only and should not be considered a substitute for professional electrical advice. Always consult with a qualified electrician before working on any electrical system. The NEC is a complex and constantly evolving document. It is important to stay up to date on the latest requirements to ensure that electrical systems are installed and maintained safely and in compliance with code. The NEC provides detailed requirements for grounding and bonding of electrical systems. These requirements are designed to protect people from electrical shock hazards and to prevent equipment damage. Proper grounding and bonding are essential for electrical safety and equipment protection. It is important to consult with a qualified electrician to ensure that electrical systems are properly grounded and bonded in accordance with the NEC. Grounding and bonding are critical aspects of electrical safety. They ensure that electrical systems operate safely and protect individuals from potential hazards. Understanding the principles and requirements of grounding and bonding is essential for anyone working with electrical systems. This narration has provided an overview of the key concepts and requirements related to grounding and bonding. However, it is important to consult with a qualified electrician and refer to the NEC for specific guidance on electrical installations.